Working with Taylor series. The piecewise function f of x equals 0 if x equal to 0 and e to the negative 1 over x squared if x is not 0. This has derivatives of all orders, and the nth derivative of f of x if value at x equal to 0 is 0 for all n. Since the Taylor's coefficients are the n derivative if value at x equal to a divided by n factorial, at x equal to 0, c sub n is the n derivative if value at x equal to 0 divided by n factorial, which is in this case 0. And so f of x is 0 plus 0x plus 0x squared, which is 0 at the Maclaurin series. This converges for every x since its sum is 0. However, this series converges to the function f of x at x equals 0 only. Thus, we see that the Taylor series generated by f of x in this example is not equal to the function f of x. Notice that the series is 0, but the function is not 0. It is 0 for x value close to 0. Let's summarize all of the important series that we have either derived or looked at already. 1 over 1 minus x is the geometric series. Its radius of conversion is r equals 1. E to the x is the series x to the n over n factorial. Its radius of conversion is infinity. Sin of x is the sum negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial, and its radius of conversion is infinity. Cosine of x is negative 1 to the n x to the 2n over 2n factorial, and the radius of conversion of cosine of x is also infinity. Notice that for cosine of x, the coefficients are even. For inverse tangent of x, it is negative 1 to the n x to the 2n plus 1 over 2n plus 1, and its radius of conversion is 1. ln of 1 plus x is negative 1 to the n minus 1, starting with n equals 1, x to the n over n, and its radius of conversion is r equals 1. And finally, the binomial series 1 plus x to the k. It is the sum of k to n times x to the n, and its radius of conversion is 1. These are some of the most commonly used series. Once we know these series, we can derive other series using this series. For example, find the Maclaurin series for f of x equals x squared times e to the x. We can take the derivative of this function successively and build the Taylor series, or we observe that we have the series representation for e to the x. E to the x is the series x to the n over n factorial, and so x squared times e to the x is x squared times the series, which is x squared times 1 plus x over 1 factorial plus x squared over 2 factorial, and so on. But we can bring the x squared inside the summation to have x squared times x to the n over n factorial, which is x to the n plus 2 over n factorial, starting with n equals 0. If we start with n equals 2, then we just simply shift the series to the left 2 units by replacing n with n minus 2. Notice that we can multiply x squared into the series to get x squared plus x cubed over 1 factorial plus x to the 4 over 2 factorial, and we observe that the exponents are now 2 more, and so that is why n plus 2. Another example, let I be the definite integral of sine of x squared dx from 0 to 1. We know that we cannot find the antiderivative of sine of x squared, but observe that sine of x is the infinite series negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. So sine of x squared is the same series, but we replace x with x squared. And this is the series negative 1 to the n x to the 4n plus 2 over 2n plus 1 factorial. And so sine of x squared is x squared minus x to the 6 over 3 factorial plus x to the 10 over 5 factorial minus x to the 14 over 7 factorial plus ... We then integrate both sides of the equation with respect to x. The antiderivative of x squared is x cubed over 3. The antiderivative of x to the 6 is x to the 7 over 7. The antiderivative of x to the 10 is x to the 11 over 11. And the factorials in the denominators are constant, so they are the same. The definite integral from 0 to 1 can be evaluated by using the fundamental theorem of calculus. The integral is f of 1 minus f of 0. But f of 1 is 1 over 3 minus 1 over 7 times 3 factorial plus 1 over 11 times 5 factorial minus, and so on, minus f of 0, but f of 0 is 0. And so we see that this is an alternating series where b sub n is approaching 0 and b sub n plus 1 is less than b sub n because the denominators are getting larger. And so this series converges. The error is using the partial sum of an alternating series s sub n is always less than the next term b sub n plus 1. And so the remainder r sub n is the absolute value of s, which is the actual sum, minus s sub n, which is the partial sum, is always less than or equal to the next term that we do not use in the partial sum. For example, the remainder using 2 terms is less than b sub 3. The remainder using 3 terms, s minus s sub 3, is less than b sub 4. b sub 4 is 1 over 15 times 7 factorial, which is 0.00001. But s sub 3 is 1 over 3 minus 1 over 7 times 3 factorial plus 1 over 11 times 5 factorial. And this is 0.31028. Another application of the Taylor series. Determine the limit at x equal to 0 of x minus sine of x over x cubed times cosine of x. We can use the L'Hopital rules because this is the indeterminate form 0 over 0. Or we can use the Maclaurin series around x equals 0. Observe the sine of x is the Taylor series x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. Cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus ... And so the limit is rewritten at x minus the series for sine of x over x cubed times the Taylor series for cosine of x. We then simplify the numerator. X minus x in the numerator cancelled out. We end up with x cubed over 3 factorial minus x to the 5th over 5 factorial plus ... And the denominator is the same. We then factor out x cubed in the numerator, and we canceled out x cubed in the denominator. The denominator is still the same. X cubed and x cubed canceled out. What is left in the numerator is 1 over 3 factorial minus x squared over 5 factorial plus ... In the denominator, 1 minus x squared over 2 factorial plus ... Since x equals to 0, any term with x in it will be 0. We end up with 1 over 3 factorial over 1, which is 1 over 6 as the limit.